Hi, I'm Nicholas, and today I'm going to be going through the 2024 WACE Chemistry multiple choice questions. So we're starting off with question 1, a pretty simple equilibrium question. So upon reading this question, there's some key things that I would first recognize, which is that there is a decrease in the mass of magnesium oxide. And I've quickly recognized that this species here is the magnesium oxide in solid form. So I'm going to go through all the options. So we've got D, the addition of a catalyst. Whilst a catalyst is very important to increase the reaction rate, ensure the reaction goes to completion, and to lower the activation energy, it doesn't affect the mass or concentration of the species. Then we have an increase in temperature. Now we know that an increase in temperature results in favouring the endothermic reaction. And in this case, the forward reaction is endothermic, and we know this because the heat value is positive. So if we therefore increase the temperature, then the forward reaction will be favoured, and that will cause the magnesium oxide and the carbon dioxide to increase in concentration. However, we're looking for a decrease in concentration, not an increase, so we can cross this option out. Then the third option is testing our understanding of what affects the K value or the equilibrium position. So solids, the addition or removal of a solid does not affect the equilibrium position. So therefore, the addition of magnesium carbonate will not have an effect. And this is largely led because solids are isolated and they can't disperse through the system. Therefore, we know that the answer is A, the addition of carbon dioxide. Now, in an exam, I would just select this answer and keep going. However, for the purpose of this video, I will explain why. So carbon dioxide as a gaseous product, an increase in carbon dioxide will result in the reverse rate being favoured, and that will therefore use up more of the magnesium oxide because the reverse reaction will be favoured. All right, now moving on to question 2. Now, for these types of questions, I like to write out all of the oxidation states. So I usually start by writing the oxidation state and then the total oxidation. So -2 for oxygen, and then 5 times -2 is -10. And then I know that to neutralise it must be +10, and then dividing that by 2 is +5. So therefore I know for part A, it's +5. The oxidation state for vanadium. Then second, so we've got -2 and -4, then +4, so we know it's going to be +4. Now for this one, we can write an equation, so we can go x, substituting x for vanadium, x minus 2 equals +1, so then we know that x equals +3, so the oxidation state of vanadium, and C is +3. This is probably the most likely answer, however, to be sure, we'll work out D as well. So I'd write an equation for this, so 4x minus 18 is equal to -2. Rearrange this to get 4x equals +16, and then x equals +4. So we know that the oxidation state will be +4 for those. So here are oxidation states. Now we're going to choose the lowest one outlined in the question, so we know the answer is going to be C. Okay, now we go on to question 3, which is kind of testing our understanding of the Bronsted-Lowry theory versus the Arrhenius theory of acid-base. So you should understand that, or we should understand that Bronsted-Lowry acid will donate a proton or a H+, and Bronsted-Lowry base, I'm just using BLA and BLB as an abbreviation here. Bronsted-Lowry base will accept a proton. Okay, so I'm quickly going to identify the underlying species, which is stated in the question, that is acting as the acid. So it's going to be this one, and its conjugate, which is very important, is this one. Now for D, we know that this cannot be the answer because right here we've got CH3 and H2, and that is accepting a proton or H+ to become CH3 and H3+, therefore acting as a Bronsted-Lowry base and not as an acid. Then C, we have NH3 losing or donating a proton or H plus to become NH2 minus. So this is definitely correct. And the second thing we're going to observe is if the species acting as the base is acting as a Bronsted-Lowry base, which in this case it is, and we know that because it's accepting the proton or H plus. So right now I'm going to state this as my answer. However, for the purpose of this video, I'll go through A and B as well. So now we've got sodium hydroxide, which is a strong base, meant to be acting as a acid. And I'm going to be looking here to look at the sodium, and I'm going to recognize that it is lost a hydroxide and not a hydrogen or a proton. Therefore, I know that this can't be the answer, because to act as a Bronsted-Lowry acid, it must lose just a hydrogen. All right, then on to A. I think this one looks correct. However, I'll explain why it's not. So this is the species in question, hydrogen carbonate, and then its conjugate base is carbonate. So we can recognize that yes, it does lose a hydrogen to become CO3 minus. So yes, it is acting as a Bronsted-Lowry acid by donating a proton. However, the other species, which is this one with chromium in it, is not accepting the proton or H plus. And the reason why, and you may question why is this the case, because the question asks, is acting as a Bronsted-Lowry acid? Yes, however, we're looking at an acid-base reaction where the base must adhere to the Bronsted-Lowry theory as well, and accept the H plus. So we know that this one is not correct. Okay, now we're on to question 4. So I would start in this question by identifying the pH and the pH for the color change and kind of what is occurring. So we know at a lower pH, which will be acidic, and then at a higher pH, it'll be more basic. So now imagining we have 4 solutions in those beakers. We've got to identify kind of which ones correspond to the respective color. So the first thing I'm going to identify is which of these so-called solutions is acidic or basic. So I know sodium ethanoate is basic. CH3COO minus Na plus. I know that potassium hydroxide is a strong base. KOH. I know that sulfuric acid is basic. Sorry, acidic. And I know that ammonium chloride is also acidic. Now, as we know that the color changes from yellow to purple, and the pH for the color changes from 7.2 to 8.8, we should therefore conclude that a pH of 7.2 corresponds to yellow. So that's an important connection to make. A pH of 7.2 corresponds to the color of yellow. So as we know, pH of 7.2 we've already identified is acidic, then we can go ahead and cross out all the options in here that are not yellow for the 2 acids. So therefore we know it's not C and it's not D. All right, now we're going to go through the same process and cross out for the bases the options that have the base as not purple. So we know that's A, does not have that as yellow. So therefore we know our final answer is B, where we have sodium ethanoate as purple, potassium hydroxide as purple, sulfuric acid is yellow, and ammonium chloride is yellow. Okay, now finally for question 5, this is just purely a theoretical question where we are essentially just looking at a systematic versus a random error. Now, I know just from memory and from theory that a systematic error will consistently be above or below. So that means, if you have error 1 will always be above the actual value. And then if you have a systematic error 2, that will be always below the actual value. Whereas if you had a random error, it could be above or below. So random error 1 could be above in the first experiment, and then below in the second experiment. So I'm just going to go ahead and then immediately select A as my answer. Okay, so we're now moving on to questions 6, 7, and 8. Now, I will quickly scan this information, and I'm going to quickly recognize that we're determining the concentration of acetic acid in vinegar. And this is through a titration, and we've got a 5-step process here. Now I'm going to read the questions to determine kind of what information I'm actually looking for. So as you can see in question 6, it doesn't actually require much information from the information that we've just read. So I'll just go through the options, and we're looking for kind of what explains it as the best indicator for this experiment. So a couple of these answers are likely to be correct, but not necessarily the best answer. So yes, the titration is between a strong base and a weak acid, as i.e. Sodium hydroxide and acetic acid. So the final solution will be slightly basic. So whilst this is correct, I feel like this is unlikely to be the answer. So I'm just going to do a little tick to show that I know that it's correct, but I won't select it yet. Okay. Now B. Phenolphthalein changes colour in the basic range at a similar pH to the equivalence point of the titration. So this is a slightly better answer, as it talks about the equivalence point, and it is correct in terms of it changes colour in the basic range. But once again, I'm just going to give it a tick and not select it yet, because I think there could be a better answer. C. Phenolphthalein is pink in the acidic range and colourless in the basic range, and so the endpoint is easy to identify. I would argue this is quite unrelated to what the question is asking, because it's asking why it's an appropriate indicator, not why it's a good indicator in general. Okay, and then D, at the equivalence point, the concentration of hydroxide is greater than the concentration of hydrogen, therefore phenolphthalein is an appropriate indicator. And its colour change also occurs at a basic pH. So this answer is incorporating the equivalence point, is giving us a metric showing the concentration, and it also talks about how the colour change occurs at a basic pH. So this combines all the relevant aspects and is therefore the correct answer, or the best answer. Okay, question 7. So this is pretty much saying it's pretty much asking you why the students, what errors the students encountered during the experiment. So by looking at this, we know that it can't be, that we don't really need to worry about 4 and 5 because they're mentioned in every answer. So we're just going to focus on 1, 2, and 3. Okay, so question part 1, step 1. So sample vinegar pipetted, and it's rinsed with the vinegar, and then deionized water is added up to the mark. And this is in a volumetric flask, so we know that this step is incorrect. Because in a volumetric flask, we're trying to determine a precise and accurate concentration or volume. So adding deionized water will not allow us to determine the accurate concentration. So that's incorrect. Then step 2, the volumetric flask was stoppered. That's fine. There's no problem with that. And the diluted solution was mixed thoroughly. Yeah, that's fine. There's no issue with that. So we can tick that. Okay, part 3, aliquots of the diluted vinegar was pipetted into conical flasks that were rinsed with deionized water, and a few drops of indicator was added. So I'm going to consider this one, and I believe this is correct. Yeah, because we can rinse the aliquots with deionized water, and there's no problem with adding a few drops of indicator. So now I can cross out any answers that don't mention part I, because we know that part I is correct. So now it's between pretty much, is it 1 and 2 or just 1, and we know 2 is not part of it, so we know that B is not right, therefore C is correct. And for the purpose of this video, I will quickly explain why 4 and 5 are also incorrect. So pretty much when we're adding the standard sodium hydroxide solution to the burette, we do not want to rinse it with deionized water. We should be rinsing it with the substance that we're delivering. And then for part 5, actually, we will cover that in the next part of the question. Okay, question 8. So pretty much we're saying which of the following does not explain why step 5 contributed to the errors. So there were insufficient titrations leading to the sample size being too small. That is true. So that's not the answer because we're explaining why it's not. So that's true. To determine if either was an outlier. Once again, this is true. This is the purpose of doing multiple titrations. And to reduce the random errors by averaging. Yes, because we've got multiple. That's therefore correct as well. Therefore, we're left with one final answer, which must be our answer, to identify the color change. So yes, there were insufficient titrations to identify the color change. Okay. And if we quickly refer back to that, is because we have insufficient titrations in step 5. Okay, part 9. So, which of the following is not a definition of an acid? So, an acid does contain a replaceable hydrogen. It's the same thing as a proton donor. It does not react with all metals, and it does produce protons when added to water. So we know that C is correct. So acids will only react with metals that are more reactive than the hydrogen that the acids produce, and that's the reason for that answer. Okay, then question 10. So sulfuric acid has a lower pH and nitric acid at the same concentration. Which of the following statements best explains this observation? So obviously the question has established that sulfuric acid has a lower pH than nitric acid, therefore is a stronger acid. So we know that this one is technically correct, and therefore we can cross this one out as well because that's technically wrong. However, we don't know that A is the best answer, which is what is highlighted in the question. We also know that D is wrong because this insinuates that nitric acid is a stronger acid because it's producing more protons in solution, which is a determinant of the strength of the acid. And then part B, option B, so sulfuric acid has more protons available for ionization than nitric acid, which is correct, and it's a better answer than part A because the number of protons that the acid produces is a determinant of the strength of the acid. So we can cross out that. We can select this, and we can cross out part A. Okay, once again, this is testing our knowledge of what determines how strong an acid is. So they're all at 25 degrees. So we're pretty much just looking at what is the highest Ka value. So the Ka value is equal to the concentration of the products divided by the concentration of the reactants. And in this case, the concentration of the products is essentially the H plus that's produced by the acid. So the extent to which it ionizes. So we're looking for the largest value. So we can pretty quickly identify that the answer here is D. Okay, now in terms of the Bronsted-Lowry theory, this is once again testing our understanding of a theoretical concept. So this is an easy question to get right if you understand the concept. So I'm going to start with the bottom for this one. So it's pretty much, the question is asking what is a limitation of the theory, and it's saying that it cannot explain the acidity and basicity of acid and base salts. Now, obviously, this is incorrect because if we have, for example, sodium ethanoate, then we know that according to the Bronsted-Lowry theory, where protons are donated and accepted, that the ethanoate could become CH3COOH, therefore accepting a proton and acting as a base. So we know this one's wrong. One limitation is that it links acids and bases into conjugate acid-base pairs rather than accounting for the transfer of protons. This is incorrect because it does link acids and bases into conjugate acid-base pairs, and that's a good thing. And it does account for the transfer of protons because the hydrogen atoms are transferred, and those are protons. So that's also incorrect. Does it explain the production of a neutral salt solution resulting from the reaction between a strong acid and a strong base? Yes, this does. In many cases, for example, if we have, I'll just pull this down here. If we have like a strong base, plus, for example, sodium hydroxide plus hydrochloric acid, we know that that will form salt, which is neutral, and water. So yes, it does that. So a limitation that it does not is incorrect. Therefore, our answer must be A. And for the purpose of this video, I'll explain why. So because the Bronsted-Lowry theory is centered around the transfer of protons, so the donation and acceptance of a H+, reactions that do not involve a H+, such as the reaction in option A, as they do not involve the transfer of protons, cannot be explained by the Bronsted-Lowry theory. Okay, question 13. Which of the following is a physical change in a closed system? So a closed system is where matter cannot escape, as well, and the question also states a physical change. So a physical change is where there's no change in the chemical composition of the substance. And just to reiterate, a closed system is a system where matter is not exchanged, but energy can be exchanged. So I'm just going to go ahead and cross out all the ones that are not a closed system. So a lake is not a closed system. Water evaporating from the skin is not a closed system. A sealed container is, and a lid on is. So we've cut it down to 2 options. Now, a physical change. So boiling water, we're just changing the activity of the particles. So I think this is the right answer, but I'm going to check A as well. Electrolyzing water in a sealed container. So if we're electrolyzing water, that's a chemical change. Therefore, we should know that the answer is A. Okay, question 14. Which of the following is a characteristic of a system at equilibrium? So at equilibrium, the rate of the forward and reverse reaction is equal and not 0. Because if it was 0, then there would be no equilibrium system. So we can cross out option A. Then the concentrations of the reactants will equal the concentration of the products. No, that's not necessarily correct. Just because the rates are equal does not mean that the concentrations are equal. The temperature of the system will rise if the forward reaction is exothermic. No, once again, this is incorrect. And this is because just because an exothermic reaction will release energy, that will be to the surroundings and not the system. So we can cross that out, and therefore we know that the colour of the system will remain constant, and this is because the rate of the forward reaction and the reverse reaction will be equal. Okay, question 15. So we're talking about a precipitation reaction here, so forming a solid between lead nitrate and potassium iodide, and at room temperature. So room temperature, at least what we consider to be room temperature, is a pretty low temperature. I think it's around like 25 or 27 degrees. So there's not that much activation energy in terms of what is provided to the reaction. So option A is most likely the right answer at this point. The reaction being very exothermic is not a correct answer, because an increased temperature will favour the endothermic reaction and a decreased temperature will favour the exothermic reaction, but the room temperature isn't long enough to be considered like a decrease in temperature. C, a large number of types of particles are involved in the reaction. I will just cross this one out. It's not really saying too much there. And then D, the need for a flame to cause the reaction to occur. Once again, this is just kind of a bit out there. It's talking about why it's rapid at room temperature. We don't need to introduce a flame. So therefore we can determine that part A is right. Okay, question 16. I like to draw these ones out. This one's a pretty simple one. thankfully. Just make sure that we're talking about straight chain here. It's very significant. Okay, especially because we've got 4 carbons. Yeah, okay, so I'm just going to draw as many out as I can. So there, and then I know I can have the bromine there, and then I can have the bromine there. And then if I imagine I put this bromine over here, that's just the same thing. So that's just the same option. And then imagine I put this bromine over here, it's just the same option. So we've really only got 2 options. And just if you can just imagine that there's hydrogens dotted around, there's 9 obviously, then that will make it a lot easier to visualize. And then we know, obviously, because we've got 2 options, that the answer must be B. So question 17. So this is a pretty simple question. It's just asking us to identify different functional groups present within the compound. So I'm just going to start from the top and look at if there's a carboxylic acid, and there's not a carboxylic acid. So I know I can cross out A, because with our carboxylic acid, we would have our carbon, oxygen, and our OH group, and that's not present in this compound. Then I'm going to look for if we have a halide group, and I can see we do because we have the chlorine here, which is a halogen connected to a carbon. So we do have a halide group. Then I'm going to see if I can identify a ketone, which will be a carbon with 2 R chains and an oxygen, and I can identify one right here, so I know that there's a ketone present in the compound. Then I'm going to look for an alcohol group, and there is not an alcohol group in this, because an alcohol group will just be a carbon with an oxygen and then just a normal R chain. And we only have carbon with an oxygen and 2 R chains, which will therefore be a ketone. So there's no alcohols. So we can cross out A and D. Now we have B and C to determine what is present. So now I'm going to look for an amide, which will be a carbon with an oxygen and then an R chain and then NH2, and we have one of these right here. So we do have an amide group present. So therefore I can determine that the answer is B. I can also cross out C because there's no carboxylate group present in this compound. Okay, question 18 is asking us to determine the lowest to highest boiling point. Now, boiling point is often determined by the type of bonding. So every compound has dispersion forces. Then most compounds have dipole-dipole, and then only some compounds have hydrogen bonding. Now, this question is actually a lot simpler than they could have made it, and I can go ahead and determine that A is the correct answer straight away. The reason why I can do this is because I know that pentane only has dispersion forces, and whilst it has the longest R chain compared to the other compounds, it does not have hydrogen bonding or dipole-dipole forces, which means that it must have the lowest boiling point. So that's why the answer is A. And the reason for the order is because butanol is an alcohol, which means that it can do hydrogen bonding because it has a hydrogen and an oxygen. And then butan-1-amine is an amine, so it can also do hydrogen bonding because it has an NH2 group. But it also has a lower boiling point than butanol, and the reason being is that oxygen is more electronegative than butan-1-amine, than the nitrogen in butan-1-amine. therefore can form stronger and hydrogen bonds more readily. And then we've got butanol, which cannot do hydrogen bonding, but it has strong dipole-dipole forces, which is why it's ranked above pentane. So I've chosen A because I've just immediately eliminated B, C, and D because we're going from lowest to highest boiling point, and we know that pentane will have the lowest boiling point because it does not have dipole-dipole or hydrogen bonding. Okay, now we're on to question 19, which is asking us about cis-trans isomerism. So cis pretty much means the same side, and then trans means on the different side of the carbon bonds. So I would just draw this out super quickly. So I would have C, H, H, and then I would have a C here, and then have a CH3. And I know that this cannot do cis-trans isomerism because we've only got one group. We need two groups for that to happen. So then I'm going to draw out B, and this one looks more promising. I'll just readjust how I've drawn this. Yeah. So yeah, this one can do cis-trans isomerism. The reason being is because we have a CH3 here and a CH3 here. So right now they're cis because they're on the same side of the double bond. But we could redraw it like this. And that would be trans because they're on a different side of the double bond. And that's the same as if we did it like this. Okay, so that's our answer, B. And we could go ahead and draw C and D out, but essentially the key thing to recognize here is that you must have two groups that can be on the same or the different side of the carbon-carbon double bond. Okay, question 20. So now we're classifying this reaction as one of these reactions. So I can immediately cross out the combustion reaction, and this is because a combustion reaction must be in the presence of oxygen, and this reaction doesn't mention that it's in the presence of oxygen, and it doesn't react with oxygen, so we know it's not a combustion reaction. We know it's not a condensation reaction because a condensation reaction will often produce water or another small molecule, and there's only one molecule, and it's the combination of the reactants. So we know it's not a condensation reaction. Then to determine if it's an oxidation reaction, we need to see if the oxidation number has changed. So the most likely oxidation number to change that I would focus on would be chlorine. So I know chlorine has an oxidation number of -1 and hydrogen has the oxidation number of +1. So if it's -1 here and it's changed, then it could be an oxidation reaction. So I'm going to go +1, +2, and then +1, +3, and then -1. So our total charge will be +4, and then that means our carbon would be +2, +2, and they're the same. So that's correct. So yeah, the chlorine has not changed its oxidation number. And if we really wanted to check, we could go +1, +2, +1, +2, and then we would have a -2, -2. And that can happen because carbons can have various different oxidation numbers. So therefore we know it's an addition reaction, which also makes sense for this reaction because we've got one reactant adding to another reactant to produce one product. So question 21. Which of the following is not a product of the oxidation of pentamono? Now pentamono is an alcohol and it looks something like this. And we know it's a primary alcohol because the carbon that the OH group is attached to is only attached to one other carbon. Now, this means that as a primary alcohol, it will be oxidized to become an aldehyde. And the aldehyde will just be the oxygen double bonded and everything else will remain the same. And you'll lose the hydrogen from the oxygen. Then this can be further oxidized to become a carboxylic acid. So as a carboxylic acid, this hydrogen here, oxygen would be introduced, and it would become something like this. So now I'm going to assess the options and look at which ones do not form part of this process. Something important to note is that during this process, carbon dioxide can also be produced. So the question is asking us which cannot be produced, so we know that carbon dioxide can be produced, so we can cross it out. Then this first option is just the aldehyde form, so that's right here. And then now we're going to go to C. And C is not part of this process, and it cannot be produced. And that's because the C represents the oxidation of a secondary alcohol. So if we drew this out, it would be that R chain, and then we would have our carbon here, double bond to an oxygen, and then this carbon would be bonded to CH3. Therefore, the original carbon would have been, this carbon here, would have been bonded to two other carbon atoms. Therefore, that would have been a secondary alcohol. So we know that this one cannot be produced by this reaction. Now, D just represents the carboxylic acid that we drew over here. Okay, now moving on to question 22. Which of the following does not contribute to the specific properties and uses of polymers in plastics? So, for polymers in plastics, there's a number of factors that can affect the properties, and these properties could include the strength, what it's used for, how resistant it is to heat, things like that. So the length of the polymer chain can definitely influence how strong it is. So we can cross that option out. The amount of cross-linking can definitely influence the durability and the structural integrity. And then the types of intermolecular forces that exist between the chains, for example, hydrogen bonding, dipole-dipole, things like that, can also influence the strength of the polymer in plastic. However, this last option, which is the correct answer in this case, is the process used to produce the polymer. This does not contribute to the specific properties. Whilst there may be byproducts, that's not contributing to the properties of the main product, which is the polymer, the plastic. Okay, question 23. This is just a theory-based question. So polytetrafluoroethene. So some of the properties that you should know about this is that it has low friction, it's chemically inert, and it also has a high heat resistance. So therefore, things like lubricants, it's great for things like lubricants, it's great for things like coating for tanks, and it's great for things like non-stick fry pans. And because this question is asking us what is not a use, we can therefore determine it can be used to insulate electric wires. It cannot be used directly for electric wires. Move on to question 24, which is asking us about addition polymers. Now, addition polymers require monomers which contain a carbon-carbon double bond. Now, whilst this benzene ring, which is present in A, C, and D, does have carbon-carbon double bonds, these are part of the benzene ring, and the electrons are actually delocalized. So they actually can't participate in addition polymerization because it'll reduce the stability of the benzene ring. So you can't count these double bonds as double bonds for addition polymerization. So I'm just going to go ahead and cross out B straight away because there's not even a double bond of any form. Then for option A, it needs to be a carbon-carbon double bond. So whilst there is an oxygen carbon double bond, this isn't suitable for addition polymerization. C does have a carbon-carbon double bond, so this is therefore our answer. And then D does not, once again, have a carbon-carbon double bond, so that can't be right. Okay, so this question asks us to differentiate between two compounds, a ketone, butane-2-one, and then butanal, which is an aldehyde. So the end of butane-2-one will look like this. And then the end of butanal will look like this. Okay, so now we're going to look at some tests. So the bromine water test, so it's a halogen, but this requires a carbon-carbon double bond like this, so that the bromine can be added in and cause a color change. So we know that because there's no double bond between the carbons in this case, there's not going to be a color change. So we know it's not the bromine water test. Then the acidified potassium permanganate solution. Now, this is quite likely to be the correct answer, and this is because this test will differentiate between ketones and aldehydes. The reason being is that it will oxidize the aldehyde, so it'll oxidize butanal, which is this one here, because the hydrogen atom in the butanal attaches directly to the carbonyl atom, so it can easily become a carboxylic acid. So it can gain this oxygen here that I've just drawn to become a carboxylic acid. Whereas with the ketone, it's much harder to become it can't become a carboxylic acid because it has a carbon-carbon bond here and a carbon-carbon bond here. So that's why the answer is B. Now the last two are also incorrect, which we've already determined anyway because we know that the B is the answer. And that's because the hydrochloric acid solution will not distinguish between them because it's neither an oxidizing or reducing agent. Then the acetic acid solution, it's often used as like a catalyst for esterification reactions, but it's not going to oxidize or specifically react to distinguish this ketone and aldehyde.